So let me start with thanking the organizers for the invitation, and I have to say I've been enjoying this conference a lot. Like I always like Matroids. I have a couple of papers on Matroids, and it's a pleasure for me in particular to attend so many excellent talks, not only on graphs but also on Matroids. Today I will be talking to something which is a rather new area in combinatorics or in graph theory. I will be talking about the limits of combinatorial objects. I will be particularly focused on limits of dense graphs. So somehow the topic of this talk is slightly different from the talks we have seen so far. So let me start with giving some motivation. And I have to say that this is more like a survey talk. I won't be doing too many technical things. I will try to occasionally hint some ideas. So in particular, you should feel very free to ask questions at any time during the talk. So let me start with the motivation, and I have to say the first two slides will be very non-mathematical. Will be kind of very abstract, and I want to explain, or at least I want to try to hint that perhaps we have been using some of the tools from the theory of graph limits, or more general from the theory of combinatorial limits in our considerations anyway, without actually thinking that there is something like a convergence or an analytic representation of a large graph or a large permutation, large partial order, large hypergraph, and so on. So the particular motivation for this line of research actually comes maybe more from computer science or statistics, where we have different types of large networks. Like, I mean, everybody talks about internet, but there's also Facebook, LinkedIn. There's, you know, whenever you go to any bank or any financial institution, they have like some kind of network representation of the data they have. And they would like to understand like what are the properties of the graphs they have. And so in particular, they would like to see, so where graphs are usually sparse, but they notice that they're not like a random cubic graph or a random graph with bounded maximum degree. There is something going on, and it would be nice to understand what's going on. And this brings natural questions how to represent a large network without actually listing all the billions or millions or whatever number of nodes, how to model such networks, and maybe like for the future use, how to extract the key properties of the network that one can use maybe by looking to the past to verify that we extracted the right properties and kind of predict how the network may evolve. I'm a mathematician, so I perhaps cannot say too much about this kind of line of motivation. For me, the motivation for looking at analytic representation of large combinatorial objects comes mostly from extremal combinatorics, where we have like various questions of the type, in particular, like I mentioned on this slide, the Turan type questions, which ask how many edges a graph without a particular subgraph can have. So one of the most classical theorems in extremal combinatorics is the theorem of Turan, that says that if you want to maximize the number of edges in your graph without creating a triangle, then the best you can do is you split your vertices into two equal parts. In case of odd number vertices, one part has one more vertex, and you put all the edges between. So basically, you take the complete bipartite graph. And likewise, if you want to maximize the number of edges without, let's say, creating a copy of K5, you take the complete four-partite graph with the parts of equal sizes. And now if somebody comes to you and asks you, okay, so how does the complete bipartite graph look like? You can describe it by what I said, but you can also say, oh, it has this adjacency matrix where you have like two subsquares are 0, they correspond to the independent set, and two subsquares are 1. So you already kind of approximate the adjacency matrix by saying, oh, actually, it has 4 parts, and 2 of the parts correspond to the independent set, and 1 of the parts correspond to the edges between, or 2 of the parts. So this kind of brings us like what we might want to, of course, like, you know, like everybody understands when I describe the adjacency matrix in this way, but we might want to come up with some theory that would, like, first of all, allow us to describe in this general or this approximate way graphs which are more complex than just the complete bipartite graph. And also we would perhaps like to have some more background, like not just, you know, drawing nice pictures that helps us, you know, to visualize the objects we work in, but actually some methods or some tools that will bring us to approach problems which are similar to these problems that I have mentioned. So let me maybe stay a little bit more still on the motivation or on the general side, because before I actually go to some definitions and some particular results. So I have to say that so what I'm going to talk will be the theory of graph limits. Some people call it an analytic approach to large graphs, or the analytic method in graph theory. And this line of research started at Microsoft Research exactly because of the motivations I mentioned on the previous slides. And I put here a couple of names of people who were at the very origin of this theory of graph limits, and I missed like many dozens of people who significantly developed the theory further. I should say that even if the theory is maybe 10 years old or 10 years plus minus something, we had seen many results which kind of naturally belong to this framework before. So some of you might be familiar with the result of Thomason, later extended by Chung, Graham, and Wilson on quasi-random graphs, which I will mention later in the talk. There have been some work on permutations, in particular due to Strongquist, who represented permutations as measures on unit squares. And all these are objects that can be formalized, in particular this representation of large permutation, and they can naturally fit the framework that I'm going to talk about. So before I actually get to the definition, I would like to say two things. So first of all, if this talk manages to ignite your interest in the theory of large graphs or theory of graph limits, combinatorial limits, there's an excellent book due to Laszlo Lovász, and which you may have a closer look and learn definitely more. In particular, this talk will not contain too many technical details, so if you want to learn more about the technical details, this is the book to look at. And also, I want to point out a distinction here, which sometimes is not that much emphasized, but so I will be talking about large graphs, and as a mathematician, I will be thinking of a sequence of graphs with the number of vertices tending to infinity, and I want to have some notion that will tell me that the graphs in the sequence will eventually look similar to each other. So basically, I want to define some kind of a metric, maybe some kind of topology on the graphs, and this relates to convergence. So on one hand, I want to be able to express that if I have a sequence of combinatorial objects, in this talk it will be graphs, but it can be some other combinatorial objects with sizes tending to infinity, they eventually look the same. So basically I want to be talking about the notion of convergence. And this doesn't require me to actually have any particular analytic representation of a large graph, large permutation, large partial order in mind. So I can be talking about convergence even without having some particular analytic representation, even if I will present one for the dense graph limits in mind. And I just want to emphasize here that having the notion of convergence and having a notion of good analytic representation for the limits, these are two separate issues. And even if in the dense setting, which I'm going to talk about today, we have a good understanding of the analytic representation. It's not the case, for instance, in the sparse setting, where we have several notions of convergences, and we don't have a good understanding of analytic representations of the limits. So this was a very general introduction. I haven't given any definition. Excuse me. But let me now actually go to some more technical stuff, and let me present the main notions for this talk. And as I said, you should feel free to interrupt me at any point. I'm very happy to take questions, answer questions if I can. If I cannot, I have some collaborators in the audience who I hope they can help me if needed. So in this talk, I will be focused on the convergence and analytic representations from dense graphs. So a dense graph for me is a graph where the number of edges is quadratic in the number of vertices. So in other words, if I pick a random pair of vertices with positive probability, they're joined by an edge. And one can define many different ways in which one can think of two graphs to be similar, and I will be mostly interested in looking at the densities of small subgraphs. And it actually turns out that this is a very robust way, because if the densities of small subgraphs agree in two large graphs, then actually, for instance, also the regularity partitions are similar and so on. So it turns out that even if this may seem like a particular choice and one may come up with many different other notions of convergences, it turns out that they're more or less equivalent. So let me define the density of a small graph H in a large graph G, and it will be, so let's say I'm interested in the density of a cherry, this graph K1, 2, and it will be just the probability that if I pick randomly 3 vertices in the large graph, I will see the cherry as an induced subgraph. So in general, if I have a k-vertex graph, its density will be the probability that if I pick randomly k vertices in my large graph, I will see this k-vertex graph as a subgraph. So this is exactly what is said here. And I will say whether a sequence of graphs is convergent if the density of every graph in this sequence converges. So what that means, the edge density converges, the density of cherries, the density of complements of cherries, the density of triangles, complements of triangles, C4s, K5s, and so on. So you may, I perhaps should also mention that in many papers on graph limits, actually, instead of requiring the convergence of density of induced subgraphs, one does require the convergence of homomorphisms or non-induced subgraphs, but these are all equivalent by simple application of the principle of inclusion and exclusion. So let me give some examples of convergent sequences of graphs, and perhaps the very simplest example is just the sequence of complete graphs. Because if I take a sequence of complete graphs, if I pick randomly k vertices, I will always see the complete graph on k vertices. So its density is 1 once n reaches at least k. So clearly the densities of all subgraphs do converge, and the sequence of complete graphs converges. Slightly less trivial example is the sequence of complete bipartite graphs, where the 2 parts are in certain ratio, maybe the ratio 1 to 1, or the ratio 1 to 2, or some other ratio. So if I take a sequence of complete bipartite graphs where the 2 parts maybe were in the same ratio, at least converge to the same ratio, to a specific ratio when this is a convergent sequence of graphs. Another example is a sequence of blow-ups. So I take a graph G and replace each vertex with a clique. If 2 vertices were adjacent, I put all the edges between. If they were non-adjacent, I put no edges between. And again, it's rather an easy exercise to convince yourself that this is a convergent sequence of graphs. A slightly less trivial example is the sequence of R-Rényi random graphs. So if I take a sequence of R-Rényi random graphs where the nth element of the sequence has n vertices, so the R-Rényi random graph is the graph with n vertices where I put an edge between 2 vertices independently of all the other edges with probability p. So this sequence of graphs is convergent. It requires like a tiny argument regarding the concentration of subgraph densities, but it's a standard martingale argument. So if you know something about like random graphs, then this should be rather on the exercise side. And I included here one more example, and now you may start object that I said I will be talking about dense graphs, but the example I included is a sequence of any planar graphs. So if you take an arbitrary sequence of planar graphs with the number of vertices tending to infinity, this is a convergent sequence in this notion, and it's for trivial reasons. Because if you have a large planar graph, and you randomly take k vertices in it, then with probability tending to 1, you will see no edges. So you will just think your graph is empty, and this is exactly the reason why this notion of convergence is not good for sparse graphs, because it brings simply no information. And you can imagine that for planar graphs, one would perhaps like to develop some different notion of convergence, likewise for graphs with bounded maximum degree, for the very same reasons that this notion of convergence will simply not extract any information about the graphs in the sequence. So this was the convergence I was mentioning. That, or maybe before I was mentioning about analytic representations, but let me maybe say a few words about some extensions. So this notion of convergence we have seen is related to the convergence of densities of substructures, and there's nothing specific about graphs in this definition. So I can define the very same notion of convergence for, first of all, like I mentioned it for undirected graphs, so I can define it for directed graphs. I can also define it for graphs where the edges are colored with finitely many or infinitely many colors. If I color with infinitely many colors, maybe what the structures that I want to distinguish is how, if I take a triangle, whether it's rainbow or it has 2 edges of the same color and one of different color is monochromatic. I can extend it to hypergraphs. One can extend it to partial orders. If I have a large partial order, I can take randomly k elements in the order and look what is the suborder defined. I can extend it to permutation, so there's a notion of subpermutation which particularly work well with this type of convergence and many other objects. We have rather good understanding of analytic representations for these combinatorial structures. So many of the results or many of the ideas that I will present in this talk, they do actually extend to these kind of combinatorial structures. And even if I will be mostly talking about dense graph convergence, let me say a few words about the sparse graph convergence. So unfortunately, the situation is not that well understood in the sparse setting. In particular, we don't have a notion of convergence that would have all the properties we wish the notion to have. Perhaps the most standard notion is the notion of Benjamin-Ishram convergence, which is the notion based on the convergence of the neighborhood statistics. However, this notion comes with the drawback that it cannot distinguish, let's say, cubic random graph and a cubic random bipartite graph, which have very different structure, for example, in the terms of the size of the largest independent set. So there have been proposed various modifications and various extensions, for example, local global convergence, due to Hatamilovas and Szegedi, partition convergence, large deviation convergence, and many others. We don't have a complete understanding of the relation between all these different notions of convergence. So in particular, we sometimes don't understand whether one implies the other. We sometimes don't have a very good understanding how we would like to have analytic representations. And actually, perhaps the biggest open problems in the theory of graph limits is so-called Aldous-Lyon conjecture, which provides necessary and sufficient conditions on the neighborhood statistics to actually correspond to a convergent sequence of sparse graphs. So let me now go maybe to a little bit more technical stuff. So I have defined the notion of convergence for dense graphs. This notion was based on the subgraph densities. And I promise, or I mentioned, that we actually do understand how to analytically represent the limit. So let me now present the standard analytic representation of sequences of dense graphs. So this is an analytic object which is called a graphon. So formally, I will define a graphon as a symmetric measurable function from the unit square to the unit interval. And I drew here some pictures. So this is a graphon. I should say that I will be always having the origin of the coordinate system in the top left corner. And the reason for that is that if you haven't seen graphons before, then one way of how to think of them is that they kind of limits of adjacency matrices. So I want to have this analogy. So if I have an adjacency matrix, let's say of this complete bipartite graph with parts of sizes with one part being 1/3, the other part being 2/3 of the vertices, this is the adjacency matrix corresponding to it, 2 squares of zeros, 2 rectangles of ones. So I will kind of think that if I look at this matrix from distance, when I will see a function which is 0 in these two parts, 1 in these two parts, and therefore I want the origin of my coordinate system to be in the top left corner, and the symmetry goes along the main diagonal as in the adjacency matrix in a graph. So now, of course, like one would like to relate these objects to sequences of convergent dense graph. So let me do it somewhat indirectly. So one of the motivations that I was mentioning at the beginning was that we want to have an analytic object that will allow us to generate a graph that resembles the graphs in the sequence. So what I'm going to do, I'm going to describe you a process. If you give me a graphon, and you think of this graphon as kind of like a high-level overview of the adjacency matrix, I will describe you a process how to generate a graph with the adjacency matrix similar to that graphon. And this process will be a process of generating a so-called W random graph. So let me now describe it. So let's say I want to generate a graph using the recipe given by the graphon W, and I want that graph to have n vertices. So the very first thing that I'm going to do, so I think of the points in the unit interval that this kind of square projects to 2 unit intervals as vertices. So I'm first going to pick n random points in the unit interval independently of each other. So let's say I want to generate a W random graph based on this graphon. Let's say I want to generate one with 20 vertices. So I pick 20 points in the unit interval independently of each other, uniformly, and maybe 7 of them lands in the first third, and 13 of them will land in the remaining 2 thirds. And then I will look at the values of the graphon for these points, and these values will give me the probability I should include an edge. So in this particular case, my graphon is 0, 1, so there's really no randomness in the second step. And if I pick 7 points from the first third of the interval and 13 points from the remaining 2 thirds, then I will just generate a complete bipartite graph K713. In general, based on this W random graphon, if I'm going to apply this process and I want to generate a W random graph with n vertices, it will have one part with n over 3 plus minus square root of n vertices, another part with 2n over 3 plus minus square root of n vertices, with probability tending to 1 because of the concentration bounds. And now let me maybe quickly go through the other examples I included here. So a graph that I will generate, a W random graph that I will generate based on this graphon, it will be just the complete bipartite graph where the 2 parts will have roughly equal sizes up to, let's say, plus minus square root of n vertices because of the concentration bounds. This graphon is a graphon which is constantly equal to P, where P is some value between 0 and 1. So usually when I will represent graphons, 0 will be represented by black, 1 will be represented by black, 0 will be represented by white, and different shades of gray will represent values between 0 and 1. So if you think, what is the W random graph that if this is my recipe, what I'm going to generate, it really doesn't matter which endpoints I'm going to pick, and I will just include each edge with probability P. So I'm just going to recover the Erdős-Rényi random graph model. And finally, if one looks at this graphon, so the graph that I would generate based on the recipe given by this graphon will be a graph which is a union of cliques, and roughly the largest clique contains half of the vertices because it corresponds to this part. The second largest, 1/4, 1/8, and so on. So this might be a good time for questions, if there are any. So let me maybe, I will ask for questions in a few minutes again. So let me maybe link now graphons to convergent sequences of graphs. So we know how, if somebody gives me this recipe, somebody gives me a graphon, I know how to generate a graph which is similar to this graphon, or has the adjacency matrix similar to that graphon. So now I want to say what can be the sequence of graphs, or convergent sequence of graphs this particular graphon corresponds to. So for that I need to think what might be a good density of a graph in a graphon. But if I generate a large W random graph, I can actually compute the expected density of the small graph in it. And it turns out it is some integral, and this integral is just the probability that, let's say I am interested in the density of the cherry, the 3-vertex graph K12 that we have seen earlier. So it's just the probability that a 3-vertex W random graph is actually the cherry. Because if you think what is the expected density of a cherry in a large W random graph, it's just the probability that a 3-vertex W random graph is a cherry. It's just like easy calculations. And this leads me to saying that the graphon W will be a limit of a convergent sequence of graphs if the density of every graph in the graphon is the limit density of that graph in the sequence. And now, of course, you start asking, like, is it true that every convergent sequence of graphs has a limit? Is it true that every graphon is a limit of some convergent sequence of graphs? So we have seen examples before, like, for example, like we would expect this graphon to be a limit of the sequence of complete bipartite graphs. I intentionally say a limit because you can imagine that if you apply some measure preserving transformation to the unit interval, you get a different graphon representing the same convergent sequence. You may think that this might be a good limit, or it's actually a limit just by computing of the sequence of Erdős-Rényi random graphs and so on. And the good news is that the answer to all these questions is positive. So what is easier to show is that if one takes a sequence of W random graphs with the number of vertices tending to infinity, when this sequence converges to W with probability 1. And this is just a standard application of tools basically from probability theory. One just needs to bound the probability of large deviations from the expected density of a small graph or small subgraph. And what is harder to show is that every convergent sequence of graphs has a limit, and this is a result due to Lovász and Szegedy. It has been kind of reproven in some different settings, and essentially the proof of this result, at least the original proof of Lovász and Szegedy, goes along looking at the regularity partitions and thinking of them as a random variable on the unit square and applying tools related to martingale conversion. So this is a result which can be explained, like very neat ideas behind it, but it's not a trivial result. It's not something that like one would perhaps be able to prove within 5 minutes. So now, what I basically now mention is that we have a great vert. We have this notion of convergence. I kind of said it's robust, even if I didn't give any evidences for it. And I represented an analytic representation of convergent sequences of dense graphs. And I said that this analytic representation is good in the sense that for every GRAPHON, we have a sequence converging to it. And for every convergent sequence, we have a GRAPHON representing it. So this was perhaps the most technical part of this talk. And what now I would like to do, I would like to mention some applications of graph limits, and then maybe like go into one particular topic which I have been working on in the last couple of years in this area. So this might be a very good time for questions if there are any. It doesn't seem to be the case. So let me go to the applications. And I want to talk about 3 particular topics or themes related to dense graph limits. And I think it's almost an obligation when one speaks about dense graph limits to mention the applications in extremal combinatorics, the closely related flag algebra method of Rasborov, which basically is a method about density calculations and using semi-definite programs to generate asymptotically true inequalities between subgraph densities. And I will talk about this method a little bit in more detail in about 5 to 10 minutes. At this point, I would like to emphasize that this is exactly an example of the phenomena I was mentioning earlier. In order to apply the flag algebra method, one needs the notion of convergence, but one doesn't need the notion of analytic representations. It's good to have a notion of analytic representation because when one can visualize things, one can think of them in maybe some kind of a broader context, but it's not necessary for the flag algebra method to have an analytic representation of convergent sequences. I will mention very briefly some applications in computer science, in particular in the area of algorithms for property and parameter testing. And I will also mention the notion of GRAPHON entropy, which tells us how many graphs are actually similar to a particular GRAPHON. So if my GRAPHON has a very rigid structure, so maybe it corresponds to the complete bipartite graph, we don't expect too many graphs to be similar to it. On the other hand, if the GRAPHON has maybe a random structure, then we expect that there will be actually a lot of graphs similar to it, because if I pick a random graph and it doesn't perhaps differ too much from the R-any random graph. And I will try to make this correspondence a little bit more precise on one of the following slides. So what I'm now going to do, I'm now going through these 3 applications, and I will say a few words about each of them. I will not go into like too many details, but I still hope that it will give you at least the feeling like what these buzzwords do mean. So let me start with the parameter testing, and I should say that property and parameter testing for dense graphs has been well understood for some time, but the theory of graph limits kind of put a new view on the results that did exist in this area. So let me talk about parameter testing. So I have, for each graph, I assign a parameter, a real number, which can, for instance, be the edge density, triangle density, or it can be some other parameters which might be related to some connectivity properties of the graph, or so on. And the idea is that somebody comes to me and gives me a very large graph, and wants me to give a good estimate of this parameter for this large graph without actually looking at the whole graph. So what I'm allowed to do, I'm allowed to look at a small sample, and usually of constant size from this large graph, and based on this small sample, of course, I cannot determine the parameter, but the hope is that I can estimate it within a small error with high probability. So formally, I will say that the parameter is testable if there exists a randomized algorithm that for every positive epsilon determines the parameter within the additive error of epsilon based on the sample of the constant size, where the constant size depends on epsilon, with the probability at least 1 minus epsilon. So somebody comes to you, tells you, I want an algorithm that will approximate the parameter with at least this probability, with at most this error. And then the algorithm should be able to say, okay, then I will need 1 million vertices to look at. The algorithm looks at 1 million random vertices, and then based on the sample says, okay, this is the value of the parameter, or this is the likely value of the parameter. And it can be shown that the parameter is testable if and only if, first of all, it's just a function of the subgraph densities. So one can, if I have a convergent sequence of graphs, the parameter will also converge in that sequence. So it makes sense to define it on the space of GRAPHON. And when this parameter is continuous on the space of GRAPHONs. And somehow, on the high level, if it's continuous, then one can kind of cover the space of all GRAPHONs or of graph limits with neighborhoods on which this parameter doesn't differ too much. And this is actually what the algorithm will kind of do. Another application or another result I want to mention is the result about GRAPHON entropy. So the idea behind is that I want to answer the question how many graphs are similar to a particular GRAPHON. So the total number of graphs, let's say I don't look at isomorphism, let's say I'm looking at labeled copies of graphs, is 2, 2, and choose 2, because I can decide freely about each edge whether I include it or not. So what I'm interested in is in determining this constant C that appears in the exponent. So whether the number of graphs corresponding or close to the particular GRAPHON is rather 2 and choose 2, or it's 2 to half and choose 2, or 1/3 and choose 2. What is the order of the magnitude? What is the base of the exponent? So I put here some terribly looking limit. So I don't know how much precise it is, but it's more or less precise. So basically this limit is the way of recovering this constant C. And what is nice is that one can define the notion of the entropy of a GRAPHON, and basically one takes the standard notion of entropy, puts the values of the GRAPHONs into it, integrate it, and this one will say is the entropy of the GRAPHON. And basically this integral is exactly this constant C that we want to recover here. So if I have the Erdős-Rényi random graphs, it has high entropy, there are lots of graphs corresponding to it. If I have a 0-1 GRAPHON, I'm integrating here the function which is 0 everywhere, the entropy is 0. But it's not surprising, because if you basically tell me my graph has this finitely many paths, you have to put all the edges between, you have to put no edges between. You really don't expect to see many graphs of that structure. You can do some local modifications, but rather of the order 2 to n, because you just decide to remove a vertex here or there, rather than of the order corresponding to really getting something which would be growing exponentially in n squared. So the next 2 slides I want to spend on the flag algebra method, and I have to say that I will actually try to give you ideas behind the method, but I will do it in a setting which actually is not too good to prove something which is meaningful. So I already mentioned that this method is to a large extent independent of graph limits. But I want to think of the method in the terms of graph limits because I already introduced them, and I think it might be somewhat easier to do so at this point. So on the very formal level, I need one object, so you know, it's the flag algebra method, so you may be asking what is the algebra in the name of the method. And it's an algebra of formal linear combination of graphs. So maybe one can take K2 minus K3. So I have a formal linear combination of graphs with real coefficients. So I have a natural addition. I have a natural multiplication by a real number. So adding just means I just add it. I should say these are finite linear combinations. Multiplying means I multiply all the coefficients. And if I have a graphon W, then I can define a homomorphism from this algebra to reals just by saying, okay, if you give me a finite combination of graphs hi with coefficients alpha I, then the value of this homomorphism for this combination will be just the sum of the densities of graph hi in the graphon W with coefficients alpha I. So every graphon gives me a homomorphism from this algebra to reals. And I just included here some examples that we kind of know what we're talking about. But the nice property of this approach is when one can also define a multiplication of two objects in the algebra. And so my aim now is to define what it means that if you give me a graph H1 and a graph H2, what should be the value of the product of the two graphs. And I will just say that it should be, I want it to be a homomorphism, so it should hold that I define this product in the way that actually the value of W for the product will be the product of the values for the two graphs in the product. So I put here a definition. I'm not sure whether you want to read it, but let me actually explain it. So imagine you want to define a product of two edges. So you want it to be, or maybe, let's say two edges. So you want it to be like that the product of two edges will be the product of the probability I see an edge and the product of the probability I see an edge. But you now need a linear combination of graphs. So what is the product of two probabilities of seeing an edge? Well, it's just the probability that if you pick randomly 4 vertices and you decide these are my first 2 vertices, you will see an edge on them. And these are my second 2 vertices, you will see an edge on them. Likewise, if my H1 is a non-edge and H2 is an edge, so what is the product of the probability if I pick randomly 2 vertices in a large graph? I will see a non-edge. And if I pick randomly other 2 vertices in my graph, I will see an edge. Well, it's the probability if I randomly pick 4 vertices and I say these are the first 2 vertices and these are the second 2 vertices, I will see an edge on the first 2 vertices and, non-edge on the first 2 vertices and an edge on the second 2 vertices. So essentially what I'm trying to say here is that if you ask me to generate 2 random copies or find 2 random copies in a large graph of a k-vertex and an l-vertex subgraph, a particular funny way of doing it is you pick first k plus l vertices, and then you say these are my k vertices and these are my l vertices. And you check when on the k vertices you see the copy of your k vertex graph, and on the l vertices you see the copy of the l vertex graph. And that's exactly what this formula says, and that's exactly if you verify these coefficients, so these coefficients correspond to the probability that if I randomly split these 4 vertices into 2 pairs, I will see 2 edges. And if I randomly split these 4 vertices into 2 pairs, I will see a non-edge and an edge on the 2 pairs. So if you maybe didn't completely digest the coefficients here, the message of the definition of multiplication is that if you give me a large graph, a very large graph, and you want me to generate a random you want me to pick a k-vertex subgraph, a random k-vertex subgraph, and a random l-vertex subgraph in it. If the graph is really large compared to k and l, these subgraphs will be disjoint. So what I can do is I instead first pick k plus l-vertex subgraph and split it into a k-vertex and an l-vertex. And this is exactly what this definition says. So once I'm equipped with this definition of multiplication, which actually behaves nicely with respect to the homomorphism I have defined, I can try to use it for something. And in particular, I can realize where the square of any real number is always non-negative. So basically, this is the whole idea behind the Fleck algebra method, that if I have properly defined the multiplication, so the value of the homomorphism for specific graphs, in particular those which are the product or some specific linear combination of graphs, in particular those that do correspond to products of two graphs, is always a non-negative number. So in particular, if I come here, when however this combination may look very weird, in any large graph, this will be a non-negative number. So if you give me any graphon, you define my homomorphism based on it, and I tell you this linear combination is greater or equal than 0, is an asymptotically true inequality between subgraph densities. And when now one can milk this idea a little bit further, so instead of taking a single graph, one can take a vector of graphs and a positive semi-definite matrix. One can evaluate this funny expression, and just by realizing what the multiplication means, when this is always also non-negative. It's just like if I have a positive semi-definite matrix, I multiply it with the same vector from the left and the right. With some transposition, maybe I always get a non-negative number. So this is a way of generating asymptotically true inequalities between subgraph densities. And the Fleck algebra method is nothing else when one formulates this as an SDP program, where one searches for asymptotically true inequalities between subgraph densities of this form. Maybe one can generate a couple of them, add them together. I have to say that I slightly simplified the things that one actually in the real program, in the real application doesn't use like this homomorphism, but some kind of rooted extensions of it. But basically, this is the main idea behind the Fleck algebra method. And I don't want to talk about the Fleck algebra method more. I mean, if you have seen it before, and now perhaps you will run to me and say that I didn't include any technical details and I said it wrongly. But I hope that if you haven't seen it before, like you maybe got some kind of the spirit of the method. And I think this might be an excellent time for questions before I go to the last part of my talk. And I noticed that I shouldn't be asking how much time do I have left, but I believe I have 5 or 10 minutes. At least So, any questions? So if there are no questions, so let me now get a little bit more specific, and I want to be talking about a particular notion from the theory of graph limits. And in order to motivate this notion, let me recall this, or let me remind this result of on quasi-random graphs due to Thomason, which was later put into some broader setting by Chung, Graham, and Wilson. And I already mentioned this result earlier. So I want to be asking when a sequence of graphs is quasi-random. So in the language we have just introduced, I am asking when a sequence of graphs converges to the constant graphon. When the limit of a sequence of graphs is the graphon, that is equal to P almost everywhere. And this classical works from the early 80s actually says that a sequence of graphs converges to the R-Rényi random graphon, or is quasi-random if and only if and now you may notice I don't write here D, but I write here H, but let's think of it for D for a while. If the density of edges converges to P, and the density of C4s converges to P to the 4. And the reason I switch from D to H is that what I want to write here actually is not the density of C4s, because I define it as an induced density, but it's the density of non-induced C4s. So it's the probability that if I pick a random injective random injective map from vertices of C4 to the graph G to the graph GI, when it's a homomorphism from C4 to the graph. So basically, I pick 4 vertices, specify a cyclic order on them, and I want to see a cycle on them. And of course, like as I mentioned earlier, these homomorphic densities can be expressed as linear combination of the induced densities, because I just look at the density of C4, K4, and K4 minus NH, put appropriate coefficients, and this will be just the density of this homomorphic density of C4. So the phenomenon that we do see here is that even in general, to specify the graphon, I need to give you all countably many subgraph densities. There are some combination, namely, if I tell you the density of K2 is P, the density of C4 is whatever it should be, maybe K4 minus an H if I want to be in the induced setting. I can specify some graphons by giving finitely many densities. And these graphons I want to talk a little bit more about, and they're called finitely forcible graph limits or finitely forcible graphons. So formally, a graphon is finitely forcible if there exist finitely many graphs and their densities that they uniquely determine this graphon. And I already gave one example. I mentioned this classical result on quasi-random graphs, which shows that the constant graphon is finitely forcible. And the extension of this result due to Lovász and Schoch says that any step graphon, any graphon which is a grid-like graphon constant on each of the cells of the grid is finitely forcible. So if you're a statistician, you would call actually these graphons stochastic block models. And there have been various other examples of finitely forcible graphons. I put here 2 more pictures. And one of the main motivation for me to look at these graphons actually comes from the extremal combinatorics. And if you recall the notion of this or these products that I was talking in relation to flag algebras. So suppose I have a graphon which is the only graphon that satisfies that the density of Hi is Di. So if I look at this sum of the squares, it will be the only graphon for which this sum of the squares is 0. Because this sum of the squares can be 0 only if and only if each summand is 0, but that means that the density of Hi is Di. But I have shown you that actually this complex sum can be expressed as some linear combination of subgraph densities because I can multiply subgraphs. But that means that a graphon is finitely forcible if and only if there exists some linear combination of the subgraph densities, that it is the only graphon minimizing this linear combination. So finitely forcible graphons are graphons which are unique minimizers for a large family of problems, or rather natural problems from extremal combinatorics. And if you look at these examples, they don't look like something like super complex, right? I mean, they look like something like, okay, this looks almost like, we can perhaps try to use this machinery to prove something in extremal combinatorics. We will talk about finitely forcible graph limits, and we will say, oh, every problem that we're interested in has a simple solution, and maybe if it's simple, we can apply some tools and prove marvelous results. And this actually has been somewhat formalized. So first of all, this simplicity of finitely forcible graphons has been formalized in several conjectures due to Lovász and Szegedy. I don't want to be talking them about in more details about these 2 conjectures right now. But essentially, they proposed what it would mean that a graphon is simple. And likewise, there was a conjecture which was sometimes formulated as a problem, as a question, and it's actually perhaps the second most cited second most cited open problems in the theory of graph limits just after the conjecture of Aldous and Lyon. And it was saying that every extremal problem of this type has a finitely forcible optimum solution. So what I showed here is that every finitely forcible graphon is a unique minimizer for some problem of this type. And this conjecture was essentially saying that one can reverse it. So if somebody comes to you and gives you a problem, minimize some linear combination of subgraph densities, there might be more graphons minimizing it. However, there will always be one that is finitely forcible. So basically the idea was that one may take a problem from extremal graph theory, then using the machinery, if this conjecture were true, show that this problem has a finitely forcible optimal solution, and maybe using some machinery from these conjectures, if these conjectures were true, showing that this graph limit must have a simple structure, and maybe one can exploit this simple structure to prove something. And now it's an advertisement break, and this is an advertisement for the next two talks. And the first news is that there's no simple structure, and Thaisa Martins, my student, she's somewhere in the audience, will be talking about that these two conjectures heavily fail, and and also the other conjecture that every problem in extremal combinatorics has a finitely forcible optimal solution is also false, and this is a more recent result with Andrej Grešik and Laszlo Miklos Lovas, so not the Lovas I was mentioning all the time in the talk, but his son. And he will be talking about this result also today. And with this, I want to thank you for your attention.
Other questions for Dan?
You talked about graphons being unique, but if you tweak it on the set of measure 0, that doesn't change. Right?
Yeah, so
can you have two different graphons that are both limits in the same sequence?
yes, so I was mentioning when I was this, at some point I made this a limit, I said. And so there's a paper due to Borgs-Chase and Lovas, and they have shown that essentially the only thing you may do is you like change it on the set of measure 0, or you apply a measure preserving transformation to the vertices. So essentially, and let me just write it here. So if this is a measure preserving transformation from a unit square to a unit square, and I have a graphon W, I can define a new graphon. By this way, and of course this graphon represents or has the same subgraph densities because I haven't done anything to it. And they showed that in some sense these are like changing on the set of measure 0 and applying this measure preserving transformation is the only thing you may do.
Maybe I have a silly question. So in these pictures of graphons, I always see the horizontal and vertical lines and diagonals in one of them. Can you get more complicated curves in them, or does that lose the linearity of?
No. So that's maybe two things or two things to this question. So I have to say that I was like defining graphons as something which is the product of two unit intervals with uniform measure and so on, or uniform probability measure. And first of all, one can generalize and think of using like general probability spaces. There's no reason to restrict oneself to a unit interval, but one doesn't get a more general notion. So for visualization, it's good to go to this unit intervals. But of course, one can have, and I think we might see some more complex structures during the next talks in this morning. So and in particular, there's also this result due to Lovas and Szegedi. So when we were looking like at finitely forcible graph limits, so they showed that if you take any polynomial, which so you may define a 0-1 graphon based on a polynomial, saying if the polynomial is negative, it's let's say 0. If it's positive, it's 1. So if you take any 0-1 graphon defined based on a polynomial on a unit square in this way, it's actually finitely forcible. So you can get like even finitely forcible graphons with much more complex structure.
Any further questions? If not, then let's have some coffee.